Testing on YouTube. Testing on YouTube. How's it going, Christopher H? YouTube is working. I just gotta wait for X. Perpetually waiting for X. That's the name of my new band. How's it going, Sarah? Let me spit out this gum. Take a sip. How's it going? Amir Hussein Zaray. Hope I said that right. How's everybody doing? Did everybody see the Optimus videos from last night? Future is coming quick, guys. It's coming quick. All right. I think this X should start momentarily here. And we're live on X. Let's double check X. Okay, it's loading, I suppose. I mean, I'm still amazed by the fact that I can sit here and talk to my computer and there's 3 different streaming services that are simultaneously piping this to the entire world. So that's pretty amazing. All right, it's working on X as well. So let's close out of all this stuff and let's get started. I've been trying to practice circular breathing so that I can indefinitely didgeridoo, but I'm not good enough to do it yet, so you're going to have to wait. All right. Welcome, everybody, to another Hoopo stream. Today, we're going to be going over this absolute monster of a paper called Meta Movie Gen. Movie Gen, a cast of media foundation models by Meta. This is a monstrous paper. It's over 92 pages long. I read the whole thing. So I went through this whole thing and I'm going to be giving you guys the highlights, my thoughts. We're going to go through it. You know, you can ask questions. But yeah, pretty impressive. It's pretty much state of the art on 20 different things. So, and they're pretty detailed. They go through everything except for the data. They do talk a lot about the data, so they talk about how they clean the data, filter the data, different problems with the data, the exact resolutions they use for the different training stages, but they don't talk about the source of the data. So I thought that was a very interesting omission from this paper. How's it going, Julien and ZZZZZ sleeping green heart. I don't know what green heart means, but hopefully it's something good. All right. We present Movie Gen, and the we here means an entire team of people, so you can scroll all the way down here to the full list of people. Look at this. Look at all these different people that are involved. This is like entire departments of people. Look at that. Blam. One interesting thing here is that in previous Meta papers, they used to tell you specifically what the different people did. So you wouldn't see how many people were in charge of data filtering, how many people in charge of architecture, how many people in charge of GPU, babysitting, you know, like down to every single detail. But it's interesting that they've kind of gotten rid of that, and now they just give you all the names and kind of one giant. It's not even ordered either. Like if you see here, you got a guy with a Z last name. Usually that guy would be last. So it's like, I guess maybe it's ordered by the first name. Okay. But yeah, maybe they realize that telling people exactly the composition of their team might not be the best thing, but I don't know. And let's get started. 1080p HD videos with different aspect ratios and synchronized audio. They do have a nice little YouTube reel here, so you can go, and this is basically just a giant collection of YouTube videos, and they're very good. You can see, so this is like a face, and you condition this video generation model with a face and then a text, such as feeding llamas or something like that. And the realism here is kind of out of control. Like, look at the stick. The llama eats the stick. Just the movement of the llama. It's so clean. Okay. Different aspect ratios, synchronized audio. A variety of different tasks in here. You have everything from instruction-based video editing, which is kind of like a new one, to text-to-video synthesis, video personalization, video editing, video-to-audio generation, text-to-audio generation, and also text-to-image generation, which is just a part of the pre-training process. But I think they also say they get state-of-the-art on that as well. So this is state-of-the-art on probably 10 to 12 different tasks. And that's kind of the stage at where we're at in the AI revolution, is that in order to get this kind of state-of-the-art results on all these different tasks, it's pretty much impossible to do with a small team anymore. So really, we've gotten to a point where rather than reading research papers where they get state-of-the-art on one task and it's a small little team of people, we're now reading research papers that are 92 pages long, get state-of-the-art on pretty much every task, and have a team of like hundreds of people, right? It's probably on the order of 100 people. So it's starting to get beyond the brain of one human, right? There isn't a single human in this entire research effort that understands everything, right? So it's kind of like any other super complicated process, whether that's the way that chips are made at TSMC or the way that Tesla car is made, right? There isn't really anybody who fully understands all the details of how a Tesla car is made. It's an organization, like a hive mind of people, and you have different specialists working on each little different part. So a little bit sad for people like myself that really want to understand every single part of it, because this is getting to the point where no one human can fully understand it, and only a hive mind of humans can create these next level AI models that are state-of-the-art on a bunch of different things. Okay. The main video model is going to be 30 billion parameters, which is actually quite small, but the reason that isn't significantly bigger is because they are going to pay for the inference budget, right? So ultimately, they want a big model to get good performance, but they don't want a model that's so big that they're going to be paying $10 for you to generate a video of a cat on Instagram, right? So they want something that's simultaneously small enough so that it's cheap enough to run at scale, but also big enough that they can get state-of-the-art. So 30 billion is what they landed on as that kind of sweet spot. Maximum context length of 73,000 video tokens. These are spatio-temporal tokens. They have their own kind of special trick there. So 73,000, kind of like a meaningless number, because what exactly is a video token? A more meaningful number here for us to understand is 16 seconds at 16 frames per second. So kind of a low frame rate there. Most videos, you kind of want around the 20 to 30 frames per second. And then if you want like super HD stuff, I think 120 frames. And then 240 frames per second is kind of capping out the human limit, right? So we still have a little bit of time to go, right? All right, let's keep going through here. Text to video generation model, MovieGen Video, is 30 billion parameters. Video to audio generation model, MovieGen Audio, is 13 billion parameters. So actually there's two different models here, right? They have a model that you type in a piece of text, it generates a video, that's 30 billion parameters. And then you can take that video and feed it into this MovieGen Audio, which is 13B parameters, and get audio corresponding to that video. We post-train the MovieGen Video to obtain a personalized MovieGen Video. This is the one that does the instruction-based video editing. So it's really a family of different models, hence why they called it a cast of media foundation models rather than just one single. The cast there is also a kind of a play on words because movies have a cast. 48 kilohertz audio. That's a high sampling frequency for audio. A lot of the audio generation papers we've been reading are usually much lower than this, like 16 kilohertz. So 48 kilohertz is some HD quality audio. You guys have probably seen these, so we can skip through. There's a lot of stuff to get through, so I'm going to be kind of flying through this. We outperform prior state-of-the-art, including Runway Gen 3, Luma Labs, and OpenAI Sora. And then they also outperform the audio generation part of this, including Pika Labs and 11 Labs. So all of these are startups, right? OpenAI is maybe a little bit more than a startup at this point, but this is state-of-the-art in all the different tasks that they introduced, and it's open source, so open source is currently the king of multimodality generative AI. Movie Gen Video. This is an interesting new notation that I saw in this paper. So this is on the order of 100 million videos. So rather than giving you the exact number of videos in the training data set or the exact number of images in the training data set, they give you the order of magnitude that it's in. So roughly 100 million videos and 1 billion images, right? They're never going to actually tell you what the images or the videos that they use are. I think partly it's because they're using other sources, right? So they're probably using YouTube, they're probably using TikTok, they're probably using these other sources, but they don't want to step into this legal landmine of admitting that they're using YouTube. So they're just going to kind of haze over that and not tell you that they're using YouTube, but I bet you they're probably using a little bit of YouTube, probably using TikTok. TikTok is probably easier to use than YouTube because TikTok is a Chinese company, right? So like, what is, right? Like, is TikTok going to try to sue Meta? Like, that's never going to work. So they can kind of use TikTok with a lower risk than using YouTube, I think. We perform supervised fine tuning on a small set of curated high quality videos and text captions. We're going to see this, but they have the same basic process of multiple training stages with a kind of a pre-training stage and then this fine-tuning stage, which we see on even language models now as well. And the really big distinction there is the quality of the data. So the pre-training is kind of like all the data, usually lower dimensional, kind of more messy. And then when you fine-tune, you're using the higher quality data. And curated there literally means curated by hand. So the quality of that very last kind of chunk of gradients that you're feeding into the model is very important. So you select the best possible data for that. 48 kilohertz high quality cinematic sound effects. And the audio model is pre-trained on the order of 1 million hours of audio, which is actually quite small, right? There's still, we're going to see this, but the Movie Gen audio feels like a generation older, right? The Movie Gen video definitely feels like state-of-the-art, not just in terms of the scale and the model architecture and all the different tricks that went into it. The Movie Gen audio feels like it's like a 2023 technology, right? And it's actually using a different architecture, slightly different training paradigm, less data, and so on. A new word that I learned when reading this paper, diegetic ambient sounds. That was a word that I did not know before reading this paper, but now I know it, and we can actually scroll down to that audio section here. They explain exactly what the fuck diegetic means. Let's get there. Should I bounce around in this? Yeah, I think I'll bounce around in this. Let's see. I highlighted it. Here we go. This. Yeah. So some sound effects, like footsteps, correlate with the low-level motion of objects in the scene, while others, like canned laughter in sitcoms, correlate with high-level semantics, such as when something funny happens, right? Imagine how intelligent a video-to-audio model needs to be to understand when specifically in the joke is the funny part and then play the laugh after that funny part, right? So getting the right audio based on video data is actually a very complicated test of intelligence. And here's this word. Diegetic audio refers to those that can be heard at the scene, such as crowd talking, newscasters speaking, music of a live band performance, birds chirping, and so on, and have a causal relationship with the video, while non-diegetic, such as narrations in documentaries or the background music or canned laughters, does not. Right? So if you think of a movie like maybe Dune, a lot of the audio in that is non-diegetic, right? It's like this orchestral music piece or kind of like weird sounds that are just kind of like ambient sounds. So there is this kind of distinction there of like, okay, well, what type of audio do you want for your video? Do you want like a music track, or do you want like the sound of the actual stuff that's happening in the scene, right? And you can see how there might be different preferences there in terms of what you want. Okay. We use a subset of videos containing humans and automatically construct pairs of image text inputs and video inputs to train the model for the personalization. They actually have a very neat little trick that they do here, borrowing from the NLP world. They do this back translation, or the equivalent of back translation for the video editing. Training recipe for Movie Gen Video. They're going to be training this not just in pre-training fine-tuning, but actually there's multiple steps within pre-training and then multiple steps within fine-tuning. And whenever they actually do the pre-training for the video generation model, they actually start it as a text-to-image. So they start with really low resolution text-to-image training, right? Text-to-image is just your standard Stable Diffusion flux, like you put a little piece of text and you get an image out of that. And they're starting at a very low resolution. And then once that is done, then they do this joint training. Joint training basically means that they're either alternating batches of text-to-image and text-to-video, and you can see they're also increasing the resolution, right? So it's not just one giant pre-training on a bunch of data and then fine-tuning on higher quality data. The quality of the data is actually scaling up over the course of training, right? So the beginning of the pre-training is the lowest quality data, and then the end of the fine-tuning is the highest quality data. And this slow ramp up in quality, you could basically think of it like a curriculum, right? It's just a more modern version of curriculum learning where you're slowly increasing the complexity of the task as you train it. Amir with a question here. Can you generate something like 10 seconds of 30 FPS? Not directly with this. So this model is only going to give you 16 FPS, but there's lots of super resolution models, right? And upscaling models. Those are pretty standard at this point, and they work pretty well, where you can just feed it a video at 30 FPS and get a 60 FPS video. You can feed a video that's 2K and get a 4K video. So I think the 16 frames and 16 seconds is some optimization was done there, and not optimization in terms of like how do we get state of the art, but optimization in terms of like, okay, the average person scrolling on a TikTok video, like what is the frames per second that is kind of not too shitty for them, but also reasonable for our inference. And then 16 seconds is kind of done in that same thing. So like the choice of 30 billion parameters, 16 seconds, 16 frames per second, I think has more to do with these kind of like user studies in terms of like what is like the minimum quality that people would be impressed by when they're scrolling on social media feeds. Okay. How's it going, Sheb, SPAC, and NLP Prompter? Joint image and video generation. We treat images as a single frame video, which allows them to use the same model to generate both images and video. And one thing we're going to see is that actually this 30 billion parameter movie gen, this text to video model, is also the state-of-the-art image generation model. So this is what I mean by this paper is state-of-the-art on pretty much everything. Joint modeling of image and video leads to better generalization, right? There's more training data to use. You can use all the images on the internet in addition to all the videos on the internet. Spatiotemporally compressed latent space. So rather than generating, for improved training and inference efficiency, rather than generating directly in pixel space, they're going to be generating in these compressed latent spaces. That's quite standard at this point. With something like Stable Diffusion or Flux, right, you're thinking about spatially compressed latents, right? So you're taking this large image and then spatially compressing it into a little latent. In this case, they're also doing that in time, right? So a video is just a sequence of frames. So you're not just compressing the space, which is the height and width of each individual frame, but you're also compressing the spatial dimension as well. And they have their own little fancy autoencoder, which they're calling the temporal autoencoder, TAE, which is going to basically compress videos into this latent space, and then you just generate in that latent space. They're going to be training this with flow matching, which is kind of the evolution of diffusion models, right? We saw, I think most modern kind of generative diffusion-y type papers use this flow matching, so that kind of makes sense. Let's keep scrolling here. Overview of the joint image and video generation pipeline. Here's a little typo, SAPSI. But you have your video, which is a sequence of frames that's getting put through this temporal autoencoder. It's turning it into a sequence of patches, right? Those video tokens that they refer to, the 76,000 video tokens over here, or 73K video tokens. And then they want a model that will be able to go from Gaussian noise into a sequence of video tokens that are actually kind of meaningful in that they can be decoded with the decoder half of the TAE into a real video. Right? So here's your actual diffusion model. It's being conditioned on this text. So this is your text is being used to condition this diffusion model, or which is a transformer. It's a little bit confusing because you can have a transformer be a diffusion model. That used to mean slightly different things, but it's all kind of converging. And this text is being encoded with 3 different text encoders. This is a pretty standard trick that we see now as well, right? Where different text encoders have slightly different benefits and negatives. They produce slightly different embeddings that are focusing on slightly different things. So using an ensemble of text encoders like this will give you a better vector that better represents the text here, right? So you have right here some vector that represents the text, and that is being used along with the sequence of tokens here that are iteratively being denoised by this transformer, which just has your standard cross attention there. The cross attention means it's a tension between this text information and the video information, or the spatial temporal information. And you also have some position embeddings as well, right, which is telling you where in the image it is, where in the text it is, and where in time it is. And all of that, run it over and over and over again, and then you eventually get a sequence of tokens that you can feed into this TAE decoder, and that produces a video. And that's the basic flow here. The temporal autoencoder compresses the input pixel space video of shape T prime by 3 by H by W, right? RGB, 3-channel videos. It has some height, has some width, has some T, which is the frames. And that this temporal autoencoder turns that into a latent X, T by C by H by W. But now this H, this W, and this T are going to be smaller. So this T by C by H by W is much smaller than this T prime by 3 by H prime by H W prime, which compresses each video basically 8x. This allows us to forego frame interpolation in simplifying our model. The TAE is alternating 1D temporal convolutions and 2D spatial convolutions. So it's basically doing spatial attention and then temporal attention. The spatial attention, then temporal attention, then spatial attention, and then temporal attention. So it's kind of 2.5D is the name that they give it later, right? It's not like full 3D, it's 2.5D. Increasing the number of channels in the latent space improves both the reconstruction and generation performance. So this C here, right, is actually smaller in the original video because you just have RGB, and then in the compressed latent video, the C is bigger. So that means that every single one of these patches is like deeper, right? But that's something that people have been doing all the way back since ConvNets. And much like they pre-train the text-to-video model initially on text-to-image tasks, the same thing is true for the TAE, where they actually initialize it using a pre-trained image autoencoder. And Meta has some of the best image autoencoders, right? They have the Dino, they have the Segment Anything image encoder. So, like, they have some really strong image encoders. So, like, they probably distilled some of that intelligence into the TAE, just to not have it start from scratch. The spot artifact. Okay, this was a cool, because this is something that we saw in papers a while ago, but now we're seeing it also in video generation. So one thing that happens with these transformer models, right, because they are these stacked transformer blocks on top of each other, is that the models figure out a way to communicate information to the blocks on top of them, right? And the way that they communicate information is that they basically take over part of the memory space that is allocated to them, right? So when one transformer layer is passing information to the next transformer layer, it wants to pass some additional kind of semantic information, right? That's basically saying, here's what this image is. And an easy way to do that is to basically take over maybe the first token or the first couple tokens and say, here, I'm going to put a bunch of information into these first couple tokens so that you can understand this video. And we saw that with the idea of VIT registers, right, where you explicitly give some amount of tokens that are used for this, right, the idea of class tokens and other things like that. But interestingly, when you don't give them that space, these models will figure out how to cheat and put that information in that little corner right here, right? So the model has made this implicit trade-off where it's like, hey, ultimately I'm being judged on the quality of this entire video, and this little corner of the video doesn't really affect the overall quality that much, at least based on the metrics that is the loss that's being used to push the gradients. So I'm going to start putting in some semantic information in there. So you can see there, that is like the AI writing in the margins of a paper, right? It's like writing little cheat codes on the margin of the paper. But we don't want these little kind of, what they call them, spot artifacts. So they actually introduce an additional loss here that will prevent the model from being able to cheat in that way, right? So the model produces latent codes with high norms. They're calling these latent dots or spots. The model learns to source crucial global information in these high norm latent dots. So they introduce this outlier penalty loss, OPL, in order to prevent that. And here's the OPL loss, which you can see it's basically just a mean of X, the average pixel, basically. Okay. We divide both the input video and the latent tensor into tiles along the temporal dimension, encode and decode each tile, and stitch the result together at the output. So even though the resolution of this is quite high, I think 1080p HD videos, they're actually doing something which you see all the time in vision language models, which is you break an image into patches, or tiles in this case, because they're kind of like higher, right? You have one, maybe 4 tiles. What do they say? Yeah, 4 tiles. And then each tile is done separately, and there's some overlap of the tile so that it doesn't look like it's 4 separate videos, right? It just looks like one continuous video. And I think the tiling is done across the time dimension, but I thought it was also the space dimension. No, it's only the time. Okay, yeah, the tiling is only along the temporal dimension. The tile size of 32 raw frames or 4 latent features. 4 latent frames. Okay, here's your flow matching, which is just a basic little explanation of effectively diffusion. In flow matching, you're generating a sample from the target data distribution by iteratively changing a sample from a prior distribution. Okay, what that means is you ultimately want a sample from the real distribution, which is the distribution of all images, aka this, but you need to start from a distribution like Gaussian noise, right? So Gaussian noise to here, right? And you can think of that there's some you're moving in the space from here to here, and that movement is defined by some vector that says, okay, you're here, you need to move this way, you're here, you need to move this way, right? So in flow matching, what you're effectively doing is you're defining this velocity, which is telling you how to move from a point in noise space to a point in the real space that you want, right? Except it's a little bit less intuitive than that because this is all being done in latent spaces. So as a human, it's really difficult to kind of understand exactly what a velocity in latent space means, but effectively that's what's happening. The model is trained to predict this velocity, which teaches it to move the sample x of t in the direction of the video sample. We use a simple linear interpolation for the optimal transport path, or the optimal transport path, which is a fancy way of saying a straight path to the goal is the fastest way to get there. So you can see here, it's basically just going from noise, and then it's taking a step over 0 to t, right? So you're iteratively removing that noise, or iteratively taking these steps, and each one of those steps you just want it to be kind of as straight into the final path, or as straight towards the final goal as you can. You're going to be training a model that has some parameters theta. This is the 30 billion parameters of the video generation model, and that model is conditioned on the image, or in the compressed latent image, and the latent text. So they take the text, turn it into this text embedding P, and then take the image, turn it into the video, turn it into that latent video X of T, and you're also giving it the time step. So how far along this denoising process are you? And you give those 3 things to this model U, and that is your flow matching model, or the model that basically predicts that, and then you can just take those steps. They use a simple first-order Euler ODE solver with a unique discrete set of n time steps tailored to our model. So the n time steps is the iterative component of the process of moving from this noise distribution to the actual image distribution, right? And zero terminal signal to noise ratio is particularly important for video generation. We saw a paper on this a while ago. Flow matching was more robust to the exact choice of noise schedules, and it outperforms diffusion losses. This is, again, something else we've seen as well. There's one other thing here that I wanted to show, because they have like a special noise schedule for this. Okay. This paper is a little bit weird because they basically like go through, they have like the mini version of the paper, which is like the first 10 pages, and then they go into like a long version where they basically just give you more details on all the different things that they talk about in this mini version. Joint image and video generation backbone. Video latent code is first patchified using a 3D convolutional layer and then flattened to yield a 1D sequence, right? They're going to be doing this with a transformer, so they need this one-dimensional sequence. Here's the kernel size of the convolution. Right, so you can see there's 3 dimensions there: time, height, and width. So the 2 spatial dimensions and the temporal dimension. And ultimately, you produce these 2x2 spatial patches. Here's the position embedding. And really the important thing to note here is that they're closely following the transformer block used in the Llama 3 paper. Right? So why is that important? Is because if you're Meta and you're going to be serving this model and training this model, you don't want to have multiple different types of architectures, right? You don't want to have one architecture for the text models, one architecture for the video generation models, one architecture for the audio generation models, right? Every single different architecture that you have to support is more complexity, more engineering effort that you have to put into training and into the inference. So by having one single unified architecture that you use for all the different modalities, it makes the training easier and it makes the inference easier, right? Because if you figure out how to do very efficient inference at scale using this specific Llama 3 architecture, then you can now use all those tricks on this video generation model. So from a efficiency standpoint, in the terms of like not wasting engineering effort and engineering time on figuring out all the different tricks for training and all the different tricks for inference, for each individual architecture, there's like a big incentive to use one unified architecture for everything, right? Unified arch for convenient scale and inference. So it's not necessarily that the transformer architecture of Llama 3 is like the most optimal architecture to do this type of video generation, but they'd rather have the same architecture for all their different models and then not have to write 3 different types of model parallelism and optimize each of those for the GPU pre-training. They'd rather just kind of use the same thing for everything. So yeah, I feel like that's a trend that we're going to see more and more often, right? I feel like Google is going to have the same kind of run into the same type of situation, and Microsoft and OpenAI are also going to run into the same type of situation where they're going to want to basically have one model architecture for all their different offerings. And there's also the additional incentive that they're all kind of using the same GPUs, right? Except for Google, that's using TPUs, but Meta and OpenAI are both using NVIDIA GPUs, right? So there's an incentive there to make a model architecture that works well for all these different use cases that is very efficient on NVIDIA GPUs. So what I actually feel like is going to happen is that there's going to be one architecture that's really optimized for pre-training and inference on NVIDIA GPUs, and then there's going to be one architecture that's optimized for training and inference on TPUs, right? So when we think about the super intelligent systems, or like 10 years from now when we have all these different services that we're using agent for this, and then we're generating video for that, like the architecture for for all those different things might actually be more similar than they are different. How's it going? Yatharth and Ares and Jay. Model not released, paper only. Yeah, they don't release the model yet, and they don't tell you what the data is, but other than that, they're much more open about all the stuff that they're doing. The spot artifact is fascinating. It's like putting a compressed encoding in the corner pixels. Yeah, this is really cool because it's like, it reminds me of like in reinforcement learning when your agent will learn some kind of weird hack to improve its score, right? So this is kind of the same thing where the models are learning a weird hack in order to improve the score by passing in information. But really what you really want them to do is to derive that information from the entire image, right? So rather than having like a little pixel here that is giving you some semantic information such as, hey, this is a dog and there's grass and this is the like lighting, right? Like rather than putting that information there explicitly, you want the model to kind of understand that just because the information is there already, right? The information is, in a way, it's like there, it's presented to you in the entire image. So thanks for asking, bro. Okay. Let's keep going here. This design choices, okay, so we were talking about using the same Llama 3 transformer architecture for this video generation and the text generation. The main difference here is full bidirectional attention instead of causal attention using language modeling. So in language modeling, you have these causal masks, which basically means that whenever you're producing tokens, you're not using the tokens in the future, right? Because it kind of doesn't make any sense. You have to produce words one at a time. But when you're dealing with images and videos, right, it's not like you want to wait, right? It's not like you want to generate this pixel only using the pixels up here, right? You also want to use the pixels down here to inform the way you're generating this pixel. So rather than doing a causal mask, which basically means you would only use the pixels up until this point to generate the next pixel, with this bidirectional attention, you also have attention going the other way, right? So like as you're to generate this pixel, you have attention over the entire image or the entire spatial temporal latents so that you can better generate each individual pixel or each individual latent. I say pixels, but it's not actually in pixel space, right? It's just that thinking about it in pixel space is more intuitive because of my limited human brain. Okay. Rich text embeddings and visual text generation. So input text prompt P is converted into a text embedding capital P. So this is this process right here where you have some text prompt P and like ASCII characters, and that gets converted into some prompt that's some latent prompt, right? Just a vector of numbers that represents that. So how are you going to do that? They're going to do that with 3 different text encoders, UL2, ByteT5, and long prompt metaclip. So long prompt metaclip is Meta's own clip encoder. And actually here in the appendix, and I did read the appendix section as well, we train our own clip style. Clip is this contrastively trained language image model that basically learns to project text and images into the same latent space. So it's a very good way of taking text and turning it into some latent that is like imagey, you know, or taking image and turning it into a latent that's kind of texty, right? I know those don't really mean anything, but they trained their own clip specifically for long prompts, because in a lot of these image or video generation models, we've seen that something that people do all the time is they synthetically generate captions that are longer, right? So rather than a video that has like a 2-sentence description, they'll synthetically generate a much longer caption that's maybe like I don't know, 10 sentences. So in order to encode those 10-sentence captions into the little vector that is the encoded prompt, now you need a slightly different clip. So they're calling this long prompt clip. And here's a little interesting tidbit here. We found that fine-tuning all the parameters in the text encoder led to rapid overfitting and suboptimal text encoding due to the fact that the uniform text style in the synthetic long image captions, right? So if you take a metaclip, which has been trained on language image or captioned images, right? A lot of captioned images, and then you fine tune it on captioned images, a much smaller captioned image data set where the captions are almost like a little bit robotic, where they have this uniform text style, then you're going to lose some of the performance of the MetaClip. So what they do is they actually freeze the image and text encoders and fine-tune the position embeddings and the biases in the text encoder. So long prompt MetaClip is just MetaClip with fine-tuned position embeddings, right? Because ultimately, the position embeddings is kind of determining where the information is in the sequence of text. I thought this was pretty cool. All right, let's go back up here. We are here. No, we are here. We are here. We concatenate the text embeddings from the 3 text encoders and then add a separate linear projection that projects them all into the same 6144 dimensional space and normalize the embeddings. Okay, so you take all your text, no matter what length of text, right? You're feeding them into these 3 different text encoders, and you're going to get a 6144 dimensional encoded text embedding. During pre-training, we sample video clips at their original FPS with a minimum of 16 FPS, and fine-tuning, we sample clips at 2 fixed FPS values, 16 and 24. So the same way that pre-training you have low resolution images and videos, and then you go into higher resolution images and videos, they're also increasing the frame rate as well. Spatially upsampled using bilinear interpolation in the pixel space to the desired output resolution. So before you feed any images into here, they're going to upsample it, right? And they're not using some kind of AI upsampler. They're literally using bilinear interpolation, which is basically just a hard-coded heuristic upsampling technique. We use a frame-wise VAE for the upsampler to improve pixel sharpness, I guess. So is this the TAE or is this just the VAE? I think they might be describing the TAE here. We train our spatial upsampler on clips of 14 frames at 24 FPS on 400K HD videos to simulate complex degradations. So they do a little bit of noising and then use that to create basically a self-supervised data set of here's a shitty video and then here's the upsampled clean video. Right? That's actually really easy to do. All you got to do is just have a bunch of clean videos and then just apply noise to them, and now you have a data set of noisy videos to clean videos. Here's the upsampler. And actually, it's not even just about creating this self-supervised task. It's also that the way that videos get compressed is actually quite known, right? So like when you're looking at a video that's shitty quality on the internet, the shittiness of that video is coming from certain types of encoding that are used to pass message or videos over the internet in a small amount of bits, right? So like we actually know the exact types of artifacts and noise that are going to exist in videos on the internet that look crappy, right? So it's not like the crappiness is being introduced in the actual camera sensor itself. The crappiness is coming from the fact that like someone had to compress this video and encode the video in order to send it over the internet. So that makes it easier. Memory constraints prohibit us from training the spatial upsampler on longer video duration. So we're still waiting on GPUs to get a little bit stronger. Now they go into the actual training itself, specifically the Meta Grand Teton AI server platform, which is 6,144 H100s GPUs. This is an absolutely monstrous system. They're using all the different tricks from their Llama 3. So you have grouped query attention instead of multi-head attention, which results in flops, and tensor memory size while also improving memory bandwidth utilization, right? So there's already this giant bag of tricks that they accumulated by training Llama 1 and Llama 2 and Llama 3. So by using the Llama 3 Llama 3 transformer architecture, they can reuse all of these same tricks for the movie generation model. Okay. Due to the quadratic nature of self-attention, which is at the heart of a transformer block, scaling to very large context lengths requires immense computation, right? The attention operation requires every single token paying attention to every single token, which means you have that quadratic scaling. So they're going to employ 3D parallelism across 3 axes. Number of parameters, input token, and dataset size, while also allowing the horizontal scale out to more GPUs. So different types of parallelism. You have tensor parallelism, sequence parallelism, context parallelism, and fully sharded data parallelism. So what is parallelism? Parallelism is basically you have 6,000 GPUs. You can take a model and split it across multiple GPUs, and that's what tensor parallelism is, right? So inside a transformer block, you have the attention operation, and then you also have this feed-forward network, which is like basically a big, fat, multi-layer perceptron. And this big, fat, multi-layer perceptron, you can shard it or split it across multiple GPUs, and that's called tensor parallelism, right? Data parallelism means that your input data itself, maybe the video is this long sequence of tokens, you can split that across multiple GPUs. So all these types of parallelisms are just fancy ways of splitting this giant block of data and this giant block of model into different GPUs, right? And then what specifically you're splitting determines the type of parallelism it is. So tensor parallelism shards the weights of the linear layers, aka the FFN, either along the columns or the rows. The cost of performing such a sharding is the addition of all reduced communication overheads in both the forward and backward passes. So it's not like you're when you shard and you split your model across multiple GPUs, that does mean you can now have a bigger model because you're not limited by the memory of each individual GPU, but the cost of that, or the problem with that, is going to be that now the GPUs are going to have to communicate with each other, right? So this all reduce operation means that the GPUs are going to have to wait for each other to send each other the information back and forth. So it's not necessarily a free lunch, but when you have 6,000 GPUs, having all these different types of parallelism is going to give you it's going to be worth it because the communication overhead is less than the negative of having to use only a very small model that can fit on one GPU and only a very small sequence that can fit on one GPU. Sequence parallelism, sharding the input over the sequence dimension for layers which are replicated and which each sequence element can be treated independently, aka the layer norm, which I think is right here. Yeah, so the layer norm right before the attention block. And then you have context parallelism, which is partial sharding over the sequence dimension for the sequence-dependent softmax attention operation. So kind of complicated, and this is just a high-level version of it too, right? It gets even more complicated if you're starting to factor in the reality of giant data centers, right? When you have 6,000 GPUs, the long tail of problems, you're going to run into them constantly, right? So if you have one GPU, the chance that your network chip fails or that your GPU fails is actually really low. But if you have 6,000 GPUs, you're almost guaranteed to be constantly running into little individual chips failing, and the fan dies, and this GPU overheats, and so on, right? And if you have a huge amount of parallelism like this, you become very susceptible to that type of errors, right? So one way to think about it is like the factory line analogy, right? If you're building cars in a production line, if there's one mistake, the entire production line has to stop, right? And you have to fix that mistake in order for the production line to continue. If you have 10 people building cars individually, if one of those guys has a mistake, the other 9 can just continue to do stuff. So there's kind of a huge amount of complexity here when it comes to these giant data centers of like accounting or designing types of parallelism that work when you have a high chance of at least one GPU failing or this particular send failing, right? Like imagine the network chip fails and then you have a bunch of GPUs just sitting there just waiting for one GPU that has one of the little shards of the model, but it's trying to send it and it keeps retrying to send it and it's just blocking the entire cluster. So I do not envy the engineers who have to deal with that. Parallelism techniques can enable training large sequence transformer models by partitioning flops and memory demands across GPUs, but introduce overheads and inefficiencies. Like the model kind of wants a hidden state. So Christopher there is referring to this here. So it's like this artifact, the spots, you can almost think of them like the model is creating a little hidden state so that it can pass information to the next transformer block, right? The model wants just a little communication channel so that it can communicate to the next layer, but we are denying it that communication channel. Pre-training data. Our pre-training data set consists of 100 million video text pairs and 1 billion image text pairs. They don't really tell you where it comes from. So I suspect it's actually TikTok and YouTube and Instagram Reels. So it's everything. And it's actually extremely heavily filtered. So later on, they have a chart here that shows you just how crazy filtered this is. Let me see if I can find it. Okay, maybe I'm not going to find it. Yeah, here it is. Look at this. Volume drop during high resolution set curation. Our data acceptance rate is less than 1%. So first they're filtering by duration. So only videos that are between 4 seconds and 120 seconds. Okay, only videos that have a resolution greater than 768 and less than 700 or less than 768 and whatever. No text, no videos with borders, have an aesthetic score higher than this number. So like, by the time you get to the end of this like data set filtering, you're only training on 1% of the data. So we still have a lot of data that we could be using, right? That's kind of the reality, is that even though this is getting state of the art, we still have so much more data that we could be feeding into these. It's just that we're very aggressively filtering to only have the highest quality of data, especially for the fine-tuning, right? Pre-training data, you can be a little bit more messy, but the fine-tuning data, the amount of filtering that is going to create that perfect fine-tuning data set is quite involved. Data curation pipeline, you have visual filtering, motion filtering, content filtering, detail generating captions containing 100 words on average. So you have a large pool of videos, and then you have multiple filtering processes until you finally get to the curated data set that you're actually going to train on. Pre-training data curation pipeline, right? And the pre-training data curation pipeline is going to be less stringent than the fine-tuning data curation pipeline. The fine-tuning data curation pipeline, you literally have humans double checking. So like at some point, a human actually looked at every single video that the fine-tuning part of the training process used. We use OCR models to remove videos with excessive text. We also perform scene boundary detection, right? So you don't want to train on a 16-second video where the first 8 seconds is one scene and then it cuts to a different scene, right? So you want it to be one continuous scene. Videos with reasonable motion based on their VMAF motion scores. Right, so think about how many videos where you have high motion, right? Like some kind of fight scene in an action movie that would instantly get filtered out. So we're not training on any action scenes from movies because they're just too jittery, too fast, right? So there's still so much more data that we could be training on here. We remove perceptually duplicate clips using similarity and copy detection embedding. Accurate and detailed text prompts for the video clips using the Llama 3 video. 70% of them are captioned with a 8B model, and 30% are captioned with a 70B model. And then you also have a classifier, which classifies the camera motions into one of 16 different classes. So zoom out, pan left, and so on. And then you're using that to, you're putting that in the caption, right? So they have a data set of here's the video and then here's the caption. They're synthetically augmenting that. And then they're also taking a model that looks at the video, tells you what type of camera motion it is, and then they add that to the prompt as well, right? So relatively involved synthetic caption creation here. We curated new videos, 80% landscape, 20% portrait. This is a little weird because I would have thought that, right, if you think about what type of video data is Meta sitting on, it's mostly kind of like Instagram pictures and Instagram Reels, right? So Instagram pictures and Reels and TikTok, those are all landscape, right? Or portrait. So 80% landscape, I feel like YouTube is landscape, right? So I don't know. I'm not like much of a social media person necessarily, so I thought it was a little bit weird that the ratio of landscape to portrait was so high on landscape. I would have assumed a company like Meta would have much more access to portrait type videos or at least square videos, so I don't know what's going on there. Maybe they're training on like Netflix as well, like video movie libraries. You know, if you're training on all the movies that humanity has created up until now, maybe that's why it's 80% landscape. So maybe it's not TikTok and it's more so like movie databases. Adding an FPS token to the text caption. There's another one. So not only are they giving you the camera motion in the caption, but they're also telling you the frames per second as well. So the caption has a bunch of metadata. Text-to-image warm-up. Directly training text-to-image or text-to-video models from scratch results in a slower conversion speed than initializing them from a text-to-image model. So they're going to start with what they call a warm-up text-to-image only training stage, which uses lower resolution and a larger batch size. Okay, so the pre-training stage is really multiple stages. You have this large batch size, low image resolution, large learning rate text-to-image stage, and then you have the text-to-image and video, what they call this joint training, where you're slowly decreasing the learning rate, and we continue to train the model and decrease the learning rate whenever the validation loss plateaus. So they're not using some kind of hard-coded learning rate scheduler, right? The learning rate scheduler is intelligent in that it's like kind of looking at the actual validation loss in order to determine when to actually drop the learning rate. And it's probably way more advanced than that as well. Fine-tuning set videos and captions are manually created. We term this stage as supervised fine-tuning, right? The supervised there basically means that you have a human that is manually creating these captions and picking the videos. That's why it's supervised. They train multiple models and combine them to form the final model through a model averaging approach. So what they mean here is that they're at the very end of the fine-tuning, right? You have this model that has come out of the pre-training, and then you're going to push gradients from this fine-tuning data set. But you're going to be pushing slightly different batches to slightly different models, and then you're going to end up with slightly different models that were trained on slightly different subsets of this fine-tuning data set. And then what you're going to do is you're going to take each of those different checkpoints and then just average them into one checkpoint, and that's going to be your final model. So it's getting quite complicated. We manually picked a few visually appealing seed videos per concept and performed video KNN, nearest neighbor search, to get a concept balanced subset of videos. Right? So the same way that whenever you were training classifiers for ImageNet, you want a nice balance of classes. You don't want too many cat images or too many dog images. Here you're kind of in a similar vein. You say, okay, well, I don't want too many videos of llamas, so I'm going to KNN or cluster the videos, and then I'm going to not cluster them based on some kind of human understandable thing, but cluster them based on some kind of semantic embedding of that video. And then we're going to make sure that within each of these cluster centers, we don't overselect one and underselect another, right? So the actual, what is it? The type of it, I don't want to say type. It's like more like the content of the video. They want that to be a very nice and even distribution over the space of all possible videos. All right, let's see. Movies have 4-second clips. It's hypnotic in nature. Yeah, I mean, the frame cutting has increased over time, right? I remember seeing a YouTube video where someone like kind of showed this, how like in older movies, like you would have a scene that would be almost like 30 seconds long, right? Like a shot that's just like 30 seconds. But nowadays, like if you watch something like a Mr. Beast video, it's like they're cutting like it's like almost like every other second. It's like 2 seconds cut, 2 seconds cut, 2 seconds cut, 2 seconds cut. And it's actually even more dystopian than that. Here, there's one kind of interesting note here. But let me see if I can find this, because this was like extremely dystopian. All right. Maybe I'll have to find it later. I think it was in the video generation here when they were talking about the video generation. I'll find it. Give me a second here, guys. Yeah, look at this. Okay, so talking about Mr. Beast and the frame rate of Mr. Beast videos and like the way that that's kind of cutting and going kind of extreme. Here's something that was interesting. Raters have a trouble staying focused comparing long videos. So obviously they're going to be using human evaluation, right? Human evaluation is kind of the gold standard. You have people looking at video 1 and then looking at video 2, and it's like, which video do you prefer? But like, humanity's dopamine is so cooked at this point that even if you're paying someone to like sit there and compare video A and video B, and we're talking about like 40-second videos, they were having a trouble because their human evaluators couldn't pay attention for 40 seconds. Right? It's like, that just gives you an idea of just how just fried humans are at this point, where like someone is literally paying you to just compare two videos that are like 40 seconds long or like 16 seconds long, and they're having a hard time staying focused. It's not like we're asking them to watch like a 3-hour movie. We're asking them to watch like these little tiny videos. Like, I don't know. I thought that was kind of hilarious that that's the point at which we're at in humanity. Okay. Let's go back here. Back here. They manually picked a couple videos. We're talking about the fine-tuning video dataset curation. Angled, lighting, vivid colors, no clutter, non-trivial motion, no camera shake, and no edited effects or overlay text. So no overlay text means it's never seen like the beginning or the end of a movie, right? Where like they show you the text, like the Harry Potter comes up on the screen and it disappears behind the cloud. Like that's removed from the training data set. Human annotators refined Llama 3 video-generated captions by fixing incorrect details and ensuring the inclusion of certain key video details. In video-supervised fine-tuning, different from pre-training that uses large-scale data, large batch sizes, and training resources, we instead use relatively a small batch size and 64 nodes, which is 512 H100 GPUs. So it's basically like two separate teams, right? They've broken up the teams into the pre-training team and the fine-tuning team. So training something on 512 H100s, you don't have to deal with the same type of shit as the people training on 64,000 H100s or 6,400 H100s, right? Like the people that are doing this pre-training on 6,000 H100s that are doing all these different types of parallelism, it's almost like a completely different world, right? They're having to deal with all these constant failures, and the communication overhead is also completely, you might even have like, it might even be multiple data centers, right? So there's some amount of communication that's going a longer distance. But when you're training on a small amount of GPUs, you don't have to deal with any of that, right? You're basically just like, oh, okay, all the GPUs are effectively all in the same room, and like the chance that one of them fails is actually relatively small. So it makes sense that you're starting to split your engineering expertise into these two different buckets. One is engineers and machine learning engineers and like GPU data center type engineer people that are very good at training on huge parallel pre-training runs. And then you have a different set of people that are doing this fine-tuning type of training, which is smaller amounts of GPUs, much higher quality data, right? You're actually literally inspecting the data to actually make sure that it's all perfect, versus the pre-training guys, they're just kind of shoveling that data. You know, they're not even looking at it. They're just shoveling it straight into the giant machine. I wonder how many people were actually involved in this. I think it's like 100 people. I don't think it's 1,000. It's definitely not. So I'm thinking in order of magnitude, right? It's more than 10, but it's less than 1,000. So I think it's on the order of 100 people were involved in the training of this. They're all Skibidi. I've seen the Skibidi like things. I don't actually know. Like, I'm a millennial and I'm too afraid to ask what Skibidi means. Do you think about rolling diffusion models as potential for arbitrary generation length? I don't know what a rolling diffusion model is, but yeah, transformers, because of the attention mechanism, they're always going to have a limited sequence length, right? But any kind of recurrent architecture, right, something like an RNN or a Mamba or an LSTM or the new liquid neural networks, right? All of those have this concept of like a fixed size hidden state that you kind of pass forward, and that means that you can effectively have an infinite context, right? The negative of that is that limited hidden state, you're never going to be able to fit all the information in there, so it's a little bit more lossy, but it's theoretically infinite. So I feel like, yes, at some point there's going to be some kind of model architecture for video generation that is going to effectively have something similar to that hidden state, right, that allows it to kind of indefinitely produce content. Do you think LLMs could generate videos natively? I mean, this is a transformer. It is a transformer generating videos, right? But a model that's trained on text tokens to produce text tokens is not going to generate videos. That doesn't really... Or are you more, BO, are you more referring to kind of the paper that we saw where there was a language model that was trained to literally output the bytes in an image? So rather than outputting pixels or outputting kind of latent tokens that are then decoded into an image, it was literally outputting the text, the like ASCII characters that are in a image. If you like open an image with a text editor, that could be kind of cool. Imagine, right, like whenever you download a movie, right, and you have like some movie on your computer that's 6 gigabytes, if you open that with a text editor, it's a bunch of little ASCII characters, right? So in theory, you could actually train some kind of transformer that just outputs those little ASCII characters, and then you could get the whole video from that. I've never seen that. We saw that with images, but we haven't seen it with videos yet. Have I seen the differential transformer thing by Microsoft? Yeah, I kind of skimmed through that one. I didn't like read that paper fully, but it seemed like people were quite excited about that. Okay, let's keep going here. Inference. Average change in model outputs between inference steps. Okay, this is the part that I was trying to get to before. The linear quadratic t-schedule. Right here. Videos generated with 250, 500, and 1,000 linear steps. So what are they talking about here with these steps? So those are, right, the fact that we are, let me note the page, we're in 17, okay. A diffusion model, right, is going from noise, x0, which is this Gaussian noise, into images or videos, or in this case, latent videos, right? So it's going from this distribution to this distribution, and it's doing it over a series of time steps dt, right? So that dt, you have to decide how big that little dt is, right? So here, when they're saying 1,000, and that t there, you're actually feeding that to the model, right? So your model is not just conditioned on the current denoise, the current state of the video, which is this little latent that's kind of partially denoised, and the prompt. You're also conditioning it on this t, right? So how do you pick the little dt, that time step? So one way to do it is, okay, you can say, we're going to have 1,000 steps, and then each little dt is just going to be 0.001, right? So you have a linear schedule for these steps, right? But they actually realized that there's a better way to do this, and they call this the linear quadratic t-schedule. A video generated with 1,000 linear steps can be precisely emulated by 25 linear steps, followed by 25 quadratic steps, predicated on the observation that the first inference steps are pivotal in setting up the scene and the motion of the video. Okay, so what that means is that at the beginning, your little dt is going to be very small, right? Because going from pure noise, right, starting from pure noise like this, the first couple steps are extremely important, right? Because they basically determine the entire scene, right? So those first couple steps, you're going to take very little tiny steps. But then once you're much further along in this time, right? Once you've already taken a couple of these little tiny dt steps, most of the scene is kind of already set, right? So you can actually go faster, right? So like the step size, you want to take bigger steps, right? Get closer to the zero. So the schedule is going to be little tiny steps when you're close to zero, and then once you get a couple of those little steps in, then you just take these big giant steps at the end, and that's what they call this linear quadratic schedule here. It emphasizes the importance of the early stages in the flow matching sequence, right? So you really want those first couple steps to be very careful. Okay. Inference prompt rewrite. Most users typically type less than 10 words, which is shorter than the average length of the training captions. We utilize Llama 3 to transform the original input prompts into more detailed ones. This is something that we actually see in most products as well, right? So like when you look at the products that are available right now, I think they list them here. So let's go to them. When you look at, here we go. No, here we go. Here we go. This one. This one. All right, I'm not finding it, but when you look at something like Runway Gen 3 or Pika or Kling or any of these like API-based video generation models, the prompt that you type is not really the prompt that's being used to generate the video, right? They're taking your little prompt of like generate an image of a cat, and they're turning it into this long training caption because the model has been trained on much longer detailed captions. So I think this is a paradigm that's going to continue, and not just in video and image generation, but in pretty much anything, right? So like even when you're interacting with a agent, right? Like you have a very small, you're giving it a very short little instruction, and then in the background, that instruction is being turned into a paragraph, and then that paragraph is what's actually being used to perform the task. So I don't know. I feel like that's pretty standard though. To improve computational efficiency, we perform a teacher-student distillation. We built a prompt rewrite teacher model based on the Llama 370B using a detailed prompt instruction and in-context learning from the foundation model training set. We fine-tuned an 8 billion Llama 3 model on this human-in-the-loop fine-tuning prompt rewrite to obtain the final prompt rewrite model to reduce the latency burden on the whole system. Okay, so if every time you want to generate a video, they have to take your shitty prompt and feed it into this Llama 370B that has this like giant prompt with instructions, and in-context learning means that inside the prompt is like, here's a short description, and here's the long description, here's the short description, here's the long description, right? Imagine them paying that amount of inference for every single video that you generate, right? That's just so much fucking money for them. They don't want to do that. So they're going to distill a tiny model. So they're going to take an 8B Llama 3 and distill it from this Llama 370B that has this giant prompt with the in-context learning examples in order to create this little tiny model that'll take your shitty prompt and turn it into a long prompt. So within this paper, there's so many of these little design decisions like this where they're being very deliberate about not just using the biggest possible model, right? It's like we're beyond... There was like a couple years ago, if you were making a paper, the sizes of the models that you chose, it was always the biggest possible model you could fucking use because you wanted to really push the boundaries of the state of the art because ultimately you were evaluated on your performance, right? But now we're starting to get to the level of AI where someone's going to have to pay for this inference budget. So if you say, hey, I have the best performance with the 70B model, like somebody's like, okay, but I'm not paying for that 70B model for every single inference. So fine tune it into this slightly shittier model. And yes, this 8B Llama 3 model is going to be shittier than this Llama 37 or Llama 370B, but it's going to be way cheaper. So we're past the point of just training the biggest possible model we can because we really, really want to push the boundaries of performance. We're now seeing the kind of reality of like, okay, most of the time you're not going to be interacting with the super smart models. You're going to be interacting with these little tiny dumb models that only have very specific tasks. Sometimes I feel like some people describe this as like the swarm intelligence approach, right? Where when we think of like the types of models that we're going to be interacting with in the future, it's not going to be like one giant model that is doing everything. It's going to be like this swarm of little tiny dumb models that have more specialized tasks. If it was a paper, God, you guys are kind of popping off here. It's hard for me to keep track of like what I've already answered. Do you think LLMs can generate videos? Okay, I answered that. You need 4 GPUs and a Threadripper, the AMD GPU or AMD CPUs. I think AMD CPUs are better than Intel CPUs at this point, which is kind of sad because what does Intel even have at this point? You know, it's like at one point they had the CPUs and they were the CPU kings, but they're not even the CPU kings anymore. Like, NVIDIA is better at GPUs than them, way better, and then AMD is better at CPUs than them. So like, what does Intel even have? In diffusion models, why do they disambiguate despite being trained with reconstruction loss? Why is detail resolved instead of averaged to an out-of-distribution blurry image? You're saying, like, why does it look like anything? You know, it's like, one way to think about it, and this is kind of, I think the 3 blue 1 brown video kind of really demonstrated this the best, is that these latent spaces, they're so high dimensional that you can fit so much information in there, right? So like, when you're talking about, this model is ultimately predicting this velocity, right? Which is kind of like you could think of it like a vector field, right? But that's a vector field that's conditioned on some specific information, specifically this prompt, right? So the knowledge of the movement that it takes, or the vector field from how to go from here to here, is only in one very little tiny corner of the total space, and that tiny corner is determined by this P, right? So it's not like there's a limited space and then you're kind of like overwriting it, and like every single image is kind of like constantly changing the other vector field so that it all kind of just looks like this. It all just turns into gray sludge, right? Because they're all kind of just overwriting. It's like the space in which this model lives is so huge that it can basically create these little tiny vector fields everywhere. And that's why models are so good at memorizing, right? That's why you can feed 1,000 examples into a transformer of this size, and it literally memorizes every single one of those 1,000 examples, right? Is that the model parameter spaces, these are so big that you can fit like so much more information than the actual data set inside each of those areas. So like, whenever the model here is conditioned on some specific time step and some specific latent image or latent video and some specific text prompt embedding, that's like such a precise coordinate location that the velocity field there is not being impacted by other shit. I don't know if that made sense, but I don't know. I recommend the 3 blue 1 brown video where he like is doing the vector math with word embeddings, right? And he's showing you how like, oh, you take the word king and you take the word queen, and the difference between those is the same as the difference between aunt and uncle or something like that, right? And then he shows you how like, when we think about it in 3 dimension, it seems like you'd overwrite the same stuff over and over again. But once you realize that it's a much higher dimensional space, like, they're not overwriting each other at all. So it travels a short distance. Yeah, or there's a lot more space to kind of store the specific little tiny vectors that you're moving, right? Because it's like, think about what each little velocity vector in this velocity field is, right? It's like this little tiny piece of information that's saying, okay, if you have this type of image and you're this far along in your noise schedule, you need to move this little tiny direction over here in order to get closer to the actual image that you want, right? That little piece of information, it's not like it's getting overwritten by all the other stuff over training. It's like still there. I don't know. I don't know if that made sense. All right. Let's see. Most companies use CPUs for processing data, but with CUDF, we wouldn't even have CPU clusters anymore. Not necessarily. I think a lot of data processing, if you can actually figure out ways to run specific types of data processing on the GPU, right? So there are ways to accelerate not just model inference and model training, right? Like, all of those things, obviously, there's ways to write them faster on a GPU than a CPU, but like, there's ways to write data processing such that it runs faster on a GPU than a CPU, especially for something like images and videos. Okay. We were here. Okay, evaluation. Human evaluation to assess the quality of generated video. So they have some humans that are basically A/B testing all these different things. Here's the different text alignment, visual quality, and realness and aesthetics. Okay. So obviously there's some like set of criteria that these humans are judging for fantastical prompts that are out of the training set distribution, e.g. depicting fantasy creatures. We define realness as mimicking a clip from a movie following a realistic art style. So summary of evaluation prompts in MovieGen Video Bench. Concepts. Person. Where, take, create. So I guess some of the most common types of information in the caption is like there is a person wearing a shirt, or there is a sun, or a person walking in the sun, taking a hat and creating a boot. So you can kind of just go back and forth between these and generate synthetic captions. Not that they're actually doing that, I'm just saying you could do that for fun. Humans are particularly skilled at recognizing temporal coherence and handling ambiguities when the context is abstract or complex. Humans are S tier at understanding and determining whether a video is real or not, right? We're extremely good at our innate understanding of real-world physics and object behavior, which is why human evaluation is the best way to do, the best way to evaluate and compare text-to-image models and text-to-video models. Automated metrics struggle to provide reliable results. Automated metrics such as FVD, Frechet video distance, and IS, inception score, do not correlate with human evaluation scores. And then things like clip, right, where you're saying, hey, does this video correspond to this caption? Like, take this caption, embed it, take this video, embed it, and then what's the distance between those? Are inherently limited by the performance of the underlying discriminative model. Right? So if your clip is shit, then the distance in clip space is also going to be shit and meaningless. We hope to publicly release our non-cherry-picked generated videos, so the ones we see now are cherry-picked. But everybody else is cherry-picking, so I don't think that's that bad. Black box commercial models offer API access. Runway Gen 3, Luma Labs, Kling 1.5, and then closed source text-to-video models such as OpenAI Sora. The publicly released videos from closed source methods are likely to be the best representative samples obtained through cherry picking. For fair comparison, we compare to OpenAI Sora by methodically manually choosing one video from 5 generated captions from MovieGen Video for each prompt. So even though they beat Sora, right? So here's the state of the art. So here's the chart that basically shows that they're state of the art in video generation. They beat all the other ones, but they kind of admitted that they're cheating because they know that OpenAI is also cheating, right? They're saying, hey, OpenAI is cherry picking their best videos. So in order to adequately compare to them, we're also going to cherry pick our best video. So it's our cherry picked best video versus your cherry picked best video, which I think is fine, right? I think it's only not fine if one of the people is not cherry picking, but all these guys are cherry picking. So I think cherry picking is okay. Here's the net win rate. I thought this was kind of like a weird win percent minus loss percent. So basically, if this number's positive, it means that they're state of the art. So the only thing that they're not state of the art in is compared to Runway Gen 3 motion completeness and compared to Kling 1.5 motion completeness and then text alignment with Kling 1.5. So kind of meaningless. For most of these, they're basically winning on these human evaluator benchmarks, which I think is enough to convince me it's state of the art. Here's a video of squirrels, puppies, Kling versus Luma versus Runway versus MovieGen. We take pre-trained checkpoints after every few thousand iterations. Validation loss is well correlated with human evaluation results, as the late checkpoints with lower validation loss perform better than the evaluations. This is a very good idea. So over the course of training, they took checkpoints. So basically, here's the validation loss, right? So this is the loss on a holdout set of data, right? So you're training on your training data set, and then you have your validation data set, which the model never sees, and then you're at every point during training, right, as you're training more and more and more and more, you're going to suddenly take the model wherever it is, and you're going to run it on the validation data set, and you're going to see what the loss there is, right? So over time, as the model gets smarter and smarter by just churning through that training data set, it's going to get better and better on this validation data set, right? And this is a loss, so a loss, lower number is better, and lower, you can see it's getting lower over the number of training iterations. So they asked themselves the question, okay, is validation loss correlated with human evaluation? So we're going to get humans to evaluate here, and then here, and then here, and then here. And if we can say that, hey, the humans prefer this to this to this to this to this, then maybe we don't even have to pay for human evaluators anymore, because we can just use the validation loss as a proxy for the human evaluation. And if human evaluation is expensive, that means that you can save money. And I mean, it's a pretty obvious conclusion, but I like that they actually went through the effort of actually showing that validation loss correlates with human evaluation score. Fine-tuning significantly improves over the pre-trained model. We kind of already knew this, right? We read the different stable diffusion papers, the flux papers, so pretty much everybody kind of understands this now, where you have your pre-training on messy data, and then you have your fine-tuning on very high quality, usually manually curated data, and that's going to significantly improve the final quality of the model. We use a 5B parameter version of MovieGen Video to produce tiny videos. Okay, so I guess they want a little tiny version, and then they basically come to the same conclusion that small models perform slightly worse than bigger models. We compare our Llama 3 Video 8B video captioning model to an image-based captioning scheme also based on Llama. Image-based captioning models captions the first, middle, and last frame. We rewrite these 3 image-based captions into a single video caption. Llama 3 Video generates captions that are preferred 67% of the time, while Llama 3 Frames rewrite captions are only preferred 15% of the time. So this is interesting, because this is kind of what, when we were, I remember using the Gemini API for that robotics project that I was working on, and inside the Gemini API docs, it actually said that the way it was doing video understanding was it was cutting the video into 1 second frames and then feeding each of those 1 seconds into some kind of VLM. So here is evidence that shows you that some kind of captioning model, which is looking at the entire video, is better than running a image captioning model on random sub-selected frames of the whole video, which again is kind of an obvious conclusion that you don't necessarily need to run the experiment to verify that, but I like that they did. Our Llama 3 based architecture outperforms the diffusion transformer on both quality and text alignment. Diffusion transformer, this is the DIT, right, from this Peebles paper. I think this is actually the guy who was at OpenAI, did Sora, and now he left, and now he's at Google. To the best of our knowledge, we find no detailed examples in the literature of scaling the DIT to very large scales. It's a little jab at Sora, because that's probably what Sora is, this diffusion transformer. We can confidently transition from the commonly used diffusion transformer to architectures more commonly used in LLMs, such as Llama 3. Ablations from important design decisions. Here's the reconstruction. So the TAE, right, is an autoencoder. So it's taking this image and it's compressing it into a lower dimensional latent representation. And then the decoder half, so the autoencoder is 2 things, right? It's this encoder and this decoder. It's going to take that compressed latent representation and then decode it back into the full image. So these 2 images should be exactly the same, or as close to exactly the same as possible. So here's what they're showing you, is that their TAE, it's compressing this, and then it's uncompressing it, and you can see it's pretty much the same image, so it's good. The 2.5D, so this is the alternating spatial and temporal convolutions rather than full 3D spatial temporal attention. While the 3D models perform slightly better than the 2.5D models, the gap in performance is small, so the improvement was not large enough to justify the larger memory and compute cost associated with a fully 3D model. So this just seems like we just need to wait a little bit and then it'll become the standard. Okay, let's keep going. Our model achieves the highest ELO rating compared to all recent state-of-the-art text-to-image methods available at the time of benchmarking. So they did another A/B comparison with human evaluators, and look at this. Ideogram, Flux, these are Midjourney v6.1. So these are some heavy hitters here, right? This is really Midjourney v6, Flux. These are like the best image generation models available. And Meta's video gen model, which is literally a video generation model, but you can just use it as an image generation model, is the state-of-the-art. So this isn't just state-of-the-art video generation, it's state-of-the-art image generation too. Let's keep going here. I think we're here. We're here. Trainable long prompt Metaclip vision encoder with a projection layer. Okay, so now we're going to go into a different section here, which is this video personalization section. Let me drink some water because I'm kind of ranting. Mind of a Fool. It's kind of incredible how much has come out since Sora was announced, but not Sora itself. Yeah, I think part of that is that Sora, the demos you saw out of Sora are a really big model, right? For something like Sora, that's what happens when they hire this guy, right? This Peebles guy. I'm not sure it's exactly that guy, but it's one of the guys. And then they tell him, and then Sam Altman comes in a room and he's like, I want you to make the best video generation model. And the guy's like, okay, I mean, I can make a really big model, but it's not going to be very good. Like, don't you want something that's a little bit smaller so that we can be a little bit more efficient at inference? And Sam Altman's like, no, we don't care about that, right? Just make it the highest quality possible thing. So the guy's like, all right, I'm going to make this fucking huge model and it's going to produce a nice video, but it's going to cost us like $300 just to run and generate one video. So this right here, this Meta Video Gen, this is a 30B model. So not only is it getting state-of-the-art and it's beating Sora, but it's also probably 10 times smaller than Sora. You know, so OpenAI kind of getting slapped right now with this. Tim Brooks, that's the guy. Okay, I'm getting my AI researchers confused. All right, but let's go to the next section here, video personalization. So this is personalized text-to-video generation. So in the demo, which they show, you basically can provide it a video. So here's like a video of one of the engineers and then say, okay, here, a person dressed in an elegant attire, and it's this guy. And then boom, there you go. This guy, person pauses to wipe sweat, boom. And this is crazy. Like, this is like a new category of things now. You know, like, look at that. You can put yourself in videos. You know, Sora is not, like, OpenAI doesn't even have this type of model. Okay, and the way they do this is you have this reference image. This is going into this long prompt Metaclip vision. You're getting some embedding that represents your face, you know, and then you have this projection layer, which is actually kind of similar to the Lava adapters, right? So this is something we see in vision language models all the time. We have these little adapters that take what's coming out of an image encoder and turn it into these tokens. Yellow frozen layers are illustrated in yellow, so all the text encoders are frozen, but they're pushing gradients into the image encoders and these projection layers. So actually very, very similar to a vision language model. I'm going to try to increase the speed here because I feel like I'm going to run out of time. So it's hard to find a data set of videos where you have a video of the person and then a picture of the person's face, right? Like that type of data set doesn't really exist. So they have to figure out how to create this data, right? So in order to create this data, they do some pretty fancy shit here. Let's see if I can get it. We extract frames at 1 second intervals, apply a face detector. We curate this training set from MovieGen video pre-training. So they basically filter, get all the ones that have humans in them, then do a face detector to cut out that face and then put that little face there. But they also do some more crazy stuff here. We further improve the video aesthetics with a high-quality fine-tuning stage. So that's the pre-training stage. Pre-training, you could just filter and cut out the human ones and okay, but that's low quality. Now for the fine-tuning, how are you going to get high-quality data sets of people's faces and a video with that person in it? Our final fine-tuning set is in the order of 1,000 high-quality videos. Annotators are asked to rate, blah, blah, blah. Where's the section? I thought there was a section on this. Cross-paired data, where the image of the face is used to condition the generation, comes from a different video clip than the video clip to be generated. Okay, so you have to make sure, so you can't just naively use a face detector to scrape the person's face and then use that to condition the video, because then your data set is just going to be like images from the video that you want to generate that look like that. But in practice, when you're actually using this model, the images that you're going to be feeding into it are not going to be coming from the same thing. Oh my God, I'm getting so lost here. Yeah, right here, right? Like this image of this guy's face is not coming from this video. So it's not like if this was your training data set, you couldn't just crop out this guy's face and then put that here and then use that to condition this, right? That's a completely different setup than you actually see in inference at test time. Oh, this is the one that was crazy here. Instruction-guided precise video editing. So instruction-guided precise video editing is you have a video like this and you're saying replace the man with a cat, and you see you have a guy riding a bicycle and now it's a cat riding a bicycle. Like this literally doesn't work. Doesn't work. It doesn't exist. There is a scarcity of supervised video editing data. There is no cat, right? A giant human-sized cat riding a bicycle. Like that video doesn't exist in the real world. So how are you going to create this? Well, you can do individual frame editing, right? You can basically use segmentation, cut it out, generate the actual image with the cat, and then use that to create the whole video. We enable input video conditioning by adding additional input channels to the patch embedder. This allows us to concatenate the latent video input with a noisy output latent video along the channel dimension. Conditioning the model on a specific editing task, our model has learned task embedding vectors. So this is something that actually is in robotics as well. Shout out to Carol Hausman. He's a guy I worked with who had this idea of task embeddings for robots, right? Where the same way that you can condition a model on a embedding here that represents this image, you can condition models on an embedding that represents a task, right? So maybe segmenting out a person and adding a cat or adding something is one type of task. Changing the background is a different type of task, right? So rather than having some hard-coded set of tasks, you basically have tasks living in this kind of nebulous task embedding space so that you can kind of interpolate between that. Video editing architecture is conditioned on the following triplet. You have the input video, obviously being fed through this temporal autoencoder, so like embedding representing the input video. The editing instruction prompt, after it's been fed through the text embedding embedding model, and then J, which is the task ID or the task embedding, I guess. Since we lack supervised video editing data, we leverage an image editing data set. So they turn an image editing data set into single frame video editing, and that's how they get the video editing. We aim to preserve the temporal consistency and generation quality of our model by simultaneously training it on both image editing and text to video generation. Blah, blah, blah. We accelerate training by alternating between image editing and video generation batches. So this is another way that they kind of got through it. And there's one more trick that they do here that's kind of cool. Right here. Back translation technique from natural language processing. So in natural language processing, way back in 2018, which feels like a million years ago, one way to create more data is to basically take your English, translate it into French, and then take that French and then translate it back to English, right? So you can, each individual pair can act as two pairs, right? So that's exactly what they're doing here. They're saying, okay, well, if we have a video of replacing the man with a cat, that means we now have a video of replacing the cat with a man. Which is kind of cool because this implies the existence of like someone having a video of a cat riding a bicycle and they're like, hey, I really want this cat to be a guy instead, which is like, what? But here you go. Replace the boy with an inflatable cat. And it's actually quite good. Like, look at that. You see this boy here, and then he's being replaced with this inflatable cat. And this is very high quality. Like, just look at the shadows on this cat. Like, we're not ready for this level of technology. Back translation technique, construct a weekly supervised video editing data set with real output videos. Okay. and they're going to compare, again, little mix of automated metrics and then human evaluated metrics. Here's what they're comparing to: Stochastic Differential Editing, SD Edit, Tuna Video, and then Runway Gen 3's Video to Video. So there really isn't like good things to compare, but I guess that there is some things. But Movie Gen Edit is preferred by human raters and human evaluation criterions by a significant margin. So we have state-of-the-art video generation, text to video. We have state-of-the-art text to image, and we have state-of-the-art video editing, which means that they also have state-of-the-art image editing. So now 4 separate state-of-the-arts in this paper, and all with human evaluators, which is the gold standard. Okay, we can skip through that. Training with back translation slightly degrades text faithfulness when compared to standard fine-tuning, but it provides very significant improvements in structure, quality, and crucially overall preference. So we'll see this back translation trick in all video-to-video models soon enough. Okay. Joint sound effect and music generation. Generating soundtracks for both the video clips and the short films. We build a single model that can perform both audio generation given a video, audio extension given a video, and can generate up to 30 seconds of audio in a single shot. Okay, so basically, what page is this, just so I know? 44. So they have Movie Gen Video, which is text to video, text to image. They have versions of Movie Gen Video that are the personalization one, and then the one that we just saw. What is it? Video personal. What is it? Instruction-based video editing. So instruction-based video editing, video personalization, those are variants of the Movie Gen Video, but then they have a different Movie Gen Audio, which is a video to audio. So you give it the video, it generates audio. But unfortunately, there's a problem with this model. And here's the problem with this model, is that it's not the Llama 3 architecture. We adopt a flow matching, so same kind of diffusion idea, but it's using the DIT. Should have been Llama 3 Arc. So you can kind of see what the story probably was, right? Where it was probably separate teams, right? You had a team that was doing this audio generation model and a team that was doing the video generation model. And the video generation model team, they decided that, hey, let's use the Llama 3 Arc, because then we can basically use all the tricks that the Llama 3 language model team used for our thing. But the team that did the audio stuff, they were like, you know what? Let's just use the DIT. So I don't think this is going to be the same. I don't think this is going to continue. I think that the next generation, the next version of this, they're not going to be using the DIT. They're going to be using the Llama 3 Arc. I feel like it seems so obvious that all of the models should be using effectively the same architecture for all the reasons that I listed before. So yeah, I think this is going to go away. So I'm just going to scroll through here because like literally none of this matters, because like one more generation and all of this crap is going to disappear because it's all going to be the same architecture. Yeah, like this is a trick that they use, like this multi-diffusion. We saw this for, I think we actually read this paper where we were generating panorama images with diffusion models, and it had to like basically do this fancy overlap where like rather than diffusing each one separately, it was like using each, like a kind of like some amount of like information was flowing between them. So like kind of unnecessary trick that we probably don't need to do once we end up using the Llama 3 Arc. Train in two stages, pre-training and fine-tuning, same objective, different data. Pre-training on 30 seconds of audio, taking 14 days on 384 GPUs, and then fine-tuning on 64 GPUs on 1 day. Some sound effects like footsteps correlate. Okay, this is what I read before with the diegetic audio versus non-diegetic audio. Build a model that generates all classes of audio jointly instead of having separate models for diegetic and non-diegetic vocal music and sound effects. Right, so the audio generation model is also, they allow it to be conditioned on text. So I think here they mention that. The fine-tuning data, right, you want the fine-tuning data to be high quality. So for the audio generation model, they fine-tune on cinematic soundtracks, right? They want that cinematic quality audio. And that's why they have such a high sampling frequency, the 46 kilohertz, is because there's no point in listening to the Dune soundtrack at 16 kilohertz. That's just like, this, it doesn't make sense. If you're going to be doing high quality audio, if you're going to be using high quality audio data, you want to keep the resolution high. Audio quality, blah, blah, blah. Here's the benchmarks. I think they also end up getting that it's better than all the existing things. They compare MovieGen Audio with 4 open source models: Diff, Folly, Follycraft, VTA, Seeing and Hearing, and then 2 black box commercial models, Pika Labs and 11 Labs. MovieGen Audio wins more on professionalness than on naturalness, indicating that MovieGen Audio learns not only to generate realistic sounds, but also professionally produced sounds, which lead to higher overall quality. So here's motion synchronized. So you can see this guy. This is a video of some person like boxing here, and you can see like the hits, like thud, 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 compared to Golf Swing, where it's just like mostly quiet, and then you have one like ding, and then it's mostly quiet. And here the waves crashing, you can see how there's like lots of noise, and then not noise, and then lots of noise, right? This is the spectrograms. Explosion, it's silent, and then suddenly boom, and then it kind of goes down. So these are all diegetic audio, I suppose. Yeah, here's what I'm saying. So TV2A versus V2A. So V2A is video to audio, where all you're giving it is the video and it's producing the audio, but you can also do TV2A, which is text video to audio. So at that point, you're not just giving it the video, you're also conditioning on some amount of text, right? So you can say penguin, and then if you just had V2A, it would just give you like penguin sounds, but you can also give it this, and then it'll not only use the video, but also use this text so that you can have a little bit more controllability about exactly what you want in the audio. Here's the Raiders having trouble watching a video longer than 10 seconds. 13B parameter model for the audio generation. Here's the little 1B parameter models that, right, Meta, I feel like is the only company, maybe it's not the only company, but they're definitely thinking a lot about the inference and like the reality that you're going to have millions of requests every single day for video, right? Like you really can't be, every single part of this pipeline needs to be efficient. So if there's any part that requires a language model, can you use a 13B language model instead of a 70B language model? Can you use a 1B language model instead of a 70B language model? So we're seeing how capitalism is providing this forcing function for people not just to kind of make the biggest models, but also really try to make these models really small. Performance generally improves across all metrics as the models scale up, but so does cost. And if you're Facebook and you have millions of users, like you really have to be aware of that. Here's the TV2A versus just V2A. Generations from the fine-tuned model are significantly better. So much like video generation or image generation, the kind of same basic idea of pre-training and then fine-tuning still applies. Here's giant related work section. It's not worth reading the related work section, guys. It's just tokens that are clogging your brain. It's like your human meat computer has such a limited budget of tokens and has such a limited capacity that I feel like I'm becoming increasingly aware of regulating my content diet. You know, the same way that they're spending more and more time being very careful about exactly what you're putting in the data set, especially for this fine tuning. I feel like I'm starting to do that as a human, you know, where it's like for example, like if there's any commercials in anything that I do, I'll like turn off the volume, right? Like I don't want to like fill my brain with commercial tokens. Pika Labs supports sound effect generation with video and optional text prompts. However, it generates audio longer than the video where the user needs to select an audio. Implies under the hood it may be using an audio generation model conditioned on a fixed number of keyframe images, which we saw is no good for image captioning video, so that's probably also not good for generating audio from that. 11 Labs leverages GPT-4o to create a sound prompt given 4 image frames extracted from the video, and then generates audio using a TTA model with that prompt. So both of the other kind of state-of-the-art video to audio models coming from Pika Labs and 11 Labs are using this kind of like individual frames into some kind of image to audio generator rather than what Meta did here where they're going from video to audio. And I agree with them that the video to audio is going to be better than like cutting out individual frames and then doing that. All right, I think we're barely going to make it here. The MovieGen cast of foundation models represents a significant improvement in text-to-video generation, video personalization, video editing, as well as sound effect and music generation. Scaling data, training compute, and model size together leads to such significant improvements. We introduce a new approach for equipping strong video foundation models with state-of-the-art video editing capabilities without relying on supervised video editing data, achieved through multitask training on image editing and video generation, followed by 2 short fine-tuning stages, one on short synthetic multi-frame editing data and another on video editing data via back translation. Currently does not support video generation, but you can see how that wouldn't be that hard to do, right? Because we saw in the video or in the voice, in the speech-to-speech paper that we read 2 weeks ago, we saw how the majority of that data set was actually synthetically generated. So voice generation is probably going to be an easier thing to create because you can create synthetic audio data sets much easier than you can create synthetic video data sets. So I think it's just a matter of time. Probably by this time next year, the MovieGen V2 and AudioGen will probably be able to also, you give it a video of like people moving their lips and it'll literally give you the audio, which means that there'll be a real-time version of that, right? Imagine a future where you can just hold up your cell phone and it can like record someone that's talking, but you can't hear them. And then that's being fed into the AudioGen model and it gives you the words. So it's like real-time lip reading, right? That's coming soon. Okay, I don't think there's anything else necessarily here. Yeah, so here basically they're saying that the Llama 3 architecture at this point, it's like they probably have like 10 people who are absolute CUDA gods, you know, and those CUDA gods are basically getting paid like $1 million salaries to take that Llama 3 architecture and figure out the like most oppressively optimal way to run that on GPUs. So the CUDA code that represents the compute of the Llama 3 architecture is probably disgustingly optimized at this point, just because they got a lot of money and they got a lot of engineers that are very good at that. What's this sentence? Yeah, this is where they're basically saying they're cherry picking to compare to Sora, but I'm okay with that because Sora's definitely cherry picked as well. All right, that's the paper. Let me sip some water. Let me answer your guys' questions, and then we'll end it. What did Pika do with the squishes and hydraulic presses? I don't know. Probably similar to the kind of like image to video stuff here, where there's text to image, or there's ways to edit images, right? Where basically you take the image, you mask out the part that you don't want with a segmentation model, then you take that Gaussian noise, and then you basically regenerate within that mask the thing, right? So you replace the hat with a cowboy hat, right? There's all kinds of image editing models, and then all you got to do is take that image editing model and now feed it into your video generation model, and there you go. Now you have a video of pre-thing and then post-thing. some kind of version of that is probably how they did the squishes and hydraulic presses, but I don't know because they didn't publish the paper, so that's also on them. If you want me to talk about your shit, you got to just publish the paper and then I'll talk about it. But if you don't publish a paper, I don't know what the fuck you're doing. RAG for tasks. Yeah, I mean, that's probably already happening. What if you want to not treat every token equally? The attention architecture is in a way not treating every token equally, right? So what attention fundamentally does is it says, okay, this token and this token, like this token and this token have a high attention score. That means these are more important, right? So like the attention architecture is fundamentally kind of focusing on the tokens that matter and ignoring the tokens that don't matter. So there is kind of that notion of like tokens are not being treated equally in a attention mechanism. Humans have non-catastrophic oblivion. I don't know what that means. Forgetting. We do kind of have catastrophic forgetting as well, right? Like if you play one video game, you'll get good at that video game. Then you play a different video game, you'll get good at that video game. And then you go back to the original video game and you're kind of shit, right? That's catastrophic forgetting. So there's humans also kind of overwrite their capacity, right? We have such a limited capacity that your brain is going to kind of overwrite previous things. Comes in early, constantly pruning. My new job, CUDA God. I mean, CUDA God, if you're a CUDA God, like that's some of the most like high paying jobs, but it's also like the darkest of the dark arts, like you really need to kind of know what you're doing and love what you're doing to be a CUDA God. I wish I was a CUDA God, but I'm definitely not. I'm just casual. Epic overview. I appreciate it. Just to mention it again, rolling diffusion is where there's more denoising on frames that are further away so you can slide over each step. Okay. Freeze from one side. Okay, I just don't know what it is. I just don't know what this is, man. Rolling diffusion. Is this your paper? Are you one of these guys? I've heard of this guy before, Tim Salamans. That name sounds familiar. Okay, here we go. Overview of the rolling diffusion. Can I understand this in 10 seconds? Input of the model contains some conditioning, okay, and a sequence of partially denoised frames. Oh, okay, so, okay, you're conditioning the model on a sequence of partially denoised frames. The model then denoises the frames by a small amount. After denoising, the sliding window shifts, and the fully denoised frames are concatenating with the conditioning. Oh, so, okay. Here's the thing. The problem with this, all right? So how is this different than what Llama is doing? The thing with the Llama is that the diffusion is all happening kind of at the same time, right? So if we go back to here, right? The entire latent video, right? So this X of T here, that's the entire video. It's the entire temporal spatial video in one latent, and you're denoising it iteratively all at the same time, right? Versus here, this is further along in the process, right? When T is going from 0 to 1, right? Time step T equals 0 to 1. What this is doing is this first frame is already at times T equals 1, basically, and this one here is almost at time T equals 0. So it's like you're basically denoising the end of the video slower than this one here. But I would say the problem with this is that you're kind of, everything becomes the first one, right? It's like this is almost the most important, like you have this Achilles heel that the very first little tiny denoising steps of this very first little frame are incredibly important, right? Which is kind of what they were saying here, right? Where they were saying, hey, there's this issue where like the first couple steps are disgustingly important, and that's why we have this linear quadratic schedule, right? Where they say that you need to be very careful because if you don't, all right, I'm not going to find it, but I feel like you want the whole video to be right. It's like, let's say you wanted this guy to be upside down or something like that. It's like, by the time you get to here, this one is going to be so much more dependent on this than if all of them were diffused kind of at the same amount of, at the same level every time. I don't know. That's my 5-second review of rolling diffusion models. I'm sorry if I didn't fully understand it. You keep sliding down. There's another image. Local diffusion time. Yeah, okay. So you see the first frames, video frame index, you have a different... Like, I see what they're doing, but it's like, is this actually better, or is it just like this? Is it worse? What's the conclusion here? Conclusion. Validating on fluid mechanic data. Rolling diffusion's natural inductive bias gets more effectively exploited when the data is highly dynamic. In this setting, rolling diffusion outperforms various existing methods. Huh. I don't know. Could be cool. Maybe we see it in the next one. Maybe we see it in the next meta paper. All right. All right, we got like 1 minute. I think I got to go. Here's the summary, and it's going to be a short one. Today we reviewed Meta Movie Gen. This is a giant-ass paper by Facebook where they basically release a state-of-the-art video generation, audio generation, video personalization, text-to-video synthesis, instruction-based video editing, all the different things, state-of-the-art. They tell you pretty much everything, except they don't release the model, and they don't tell you what data set they trained on. But other than that, this is like a giant, comprehensive overview of pretty much everything you could ever want to know about training, evaluating, video generation and audio generation models. I'll leave it at that. Thanks, Daddy Zuckerberg, for giving us this information. Hope you guys have a good weekend. Thanks, everybody. Thanks, Mind of a Fool, God Buddy, Saskia, Sarah, Z, God Buddy, NLP, Yatharth, Aries, Sid, Marine Power, Chicken P, BO, Sotaki, Christopher H, Emily, The Big Flat Now, Jai Kai, Aries, Yatharth, Triple Z's, Spac, Sheb, Sarah. Thanks, everybody, for listening. Hope you guys have a great weekend, and see you guys later.